Hello again. This is the video on assignment solving. This is a video on assignment solving for week 11. It will be uploaded as always after the deadline of the assignment. If you remember, week 11 lectures dealt with symbolic and concolic testing, and so this assignment is on the questions related to symbolic and concolic testing. So as we did for other lectures, I'll walk you through question after question, explain the question and also show the answer to you. So the first question in the video was the following, in the assignment, was the following. Which of the following is a list of disadvantages of symbolic testing? As I told you, symbolic testing was introduced in the year 1976, but didn't scale up to see the light of the day till the past decade or so, mainly because it had several disadvantages, even though it was a novel technique. So 4 options were given to you. First one was unsolvable path constraints, procedure calls with inaccessible code, programs with very large lines of code. Second one was nonlinear path constraints, programs with very large lines of code. Third one was large number of path constraints, procedure calls with inaccessible code, programs with lots of decisions. Finally, again the same thing, but 2 of the choices that were repeated. So while choosing, you might be confused to think that second one is the correct answer. But in options like this, when there is an overlap on the choices that are available, the usual correct thing is to show the complete list of disadvantages. So from that point of view, first option is the correct answer, because all 3 listed here are disadvantages, unlike option 2, which lists only 2 of the disadvantages, and option 4 and 3 are not really disadvantages, because programs with lots of decisions and a large number of path constraints practically mean the same, and that just means that a longer path constraint, that should not be a disadvantage of symbolic testing. What is a disadvantage is that if you get a path constraint that's not solvable, cannot be solved by a constraint solver, we can't generate test cases. And if you have procedure calls whose code is not accessible, then you have a problem, because you don't know what additional path constraints should come from the procedure. So the first one is the correct answer. Second question was, what does concolic testing stand for? It was a simple question. 4 options were given. It just stands for concrete testing, concrete plus symbolic testing, concrete testing without symbolic execution, or none of the above. So the correct answer is option 2, because concolic, not a first class English dictionary word, but is derived with a combination of concrete and symbolic. Tries to do symbolic execution whenever it encounters one of the disadvantages that we discussed in question 4. It tries to substitute it with concrete values, hence the term concrete plus symbolic or concolic. So the correct answer is option number 2. So the third question is, symbolic path constraint is which of the following? Is it a propositional logic formula? Is it an arbitrary first order logic formula? Is it a first order logic formula that does not have any quantifiers? Quantifiers are for all and there exists. Or is it a higher order logic formula? By higher orders, I mean you could quantify over functions and relations also, apart from quantifying over variables. The correct answer is third option. Why is it third option? It's definitely a first order logic formula, not a propositional logic formula, and not a higher order logic formula. It's first order because you have predicates or functions over several variables that the program is working on. Program has such functions. So it's a first order logic formula. In addition to that, there is no scope for getting path quantifiers in the path constraint. You can't put there exists and for all. So it's a first order logic formula without quantifiers. That's the correct answer. Third option. Fourth question says, which of the following best represents a symbolic variable? You remember what a symbolic variable in symbolic execution was? So I want to be able to execute the program not with concrete values but symbolically. Symbolic variables help me to execute a program symbolically, and throughout my lectures we just gave them some variable names. We call them alpha and beta, or capital X and capital Y. But if you have to actually go ahead and implement a symbolic execution tool like Dart or Crest or Qt, how would you represent a symbolic variable? That's the question about. So there were 4 options again given here. It is the memory address of a variable. It is just a variable name. It is a pointer to a variable. The 4th answer is none of the above. The correct option is the first one, memory address of a variable. So memory address of a variable can be thought of as a placeholder value that represents the variable symbolically. It can be substituted by a concrete test value that satisfies the constraints that the symbolic value satisfies. The correct answer is memory address of a variable. Question number 5. In the tool Dart that we saw, which we discussed from the Dart paper, the following question is about that. It asks if the concrete values are substituted instead of symbolic values in which of the following cases. They are substituted randomly. Concrete values are substituted when path constraints are linear. Concrete values are substituted when path constraints are non-linear. Or the 4th option, symbolic and concrete values are considered in every alternate run. Which is the correct answer? The correct answer is the 3rd option, which is concrete values are substituted by the Dart tool when path constraints are non-linear. Why is this a correct option? If you remember, the time in which a paper like Dart and tool was developed was in 2004-2005. At that time, when it comes to constraint solving, there were no good constraint solvers that could handle non-linear path constraints. As I told you during the lectures in that week, the generic problem is an undecidable problem. So in Dart, they took a decision that whenever path constraints are non-linear, you could substitute it with concrete values and go ahead and drop symbolic execution in such cases. So the correct answer is non-linear path constraints, or option 3. So for the remaining 5 questions in the assignment for last week, I had given you a piece of code, asked you to draw the symbolic execution for that piece of code, and there were questions about symbolically executing that code. Like we saw throughout this course, this is not a complete piece of code, it's just a fragment of the code. We'll first go through the code that was given in the lecture and see what it is doing. So it took 2 integer variables x and y. There was an if statement which said x is greater than y. Then you do these 3 statements. I'll come back in a minute and tell you what these 3 statements are. And then it says if x minus y is greater than 0, then you assert false. So there are 2 if statements, one nested inside the other, and then if reaching line number 6 means that you have reached an error. Assert false means that I am telling that the program has an error. Interpret it that way, that you are asserting something that is wrong if you reach this line number 6, which means the program has an error. So what do these lines 2, 3 and 4, the program statements do? So what it says is if x is greater than y, let's say x is 5, y is 2, just as an example. The first one does x is x plus y, so it adds it, so makes x 7 as per our values, and then it does y is x minus y. So what is x now after the previous statement? It is x plus y. So you substitute it here, you will get x plus y minus y. The plus y and minus y will get cancelled, and y will take the value of x. The 4th line says x is x minus y. So what does x is x minus y mean? This x here on the right hand side is actually x plus y, and the y is actually x. So what it will do is x is x plus y minus x. The x and minus x will again get cancelled. X will become y. So basically lines 2, 3 and 4 swap the values of x and y. I hope that is clear. It's not the most obvious way of swapping. The most obvious way of swapping that we know is to have a temporary variable, assign one value to the temporary, and then do this. This just does swapping in a slightly different way. That doesn't matter to us, but it basically swaps x and y. That's all it does. And it says if the swapped values of x and y are such that x minus y is greater than 0, then for some reason I have hit an error. So this was the example program fragment that was given, and then you were asked to draw the symbolic execution tree for this program. Based on the symbolic execution tree, there were 5 more questions asked in the assignment. So here were some guidelines on drawing the symbolic execution tree. Symbolic execution tree is like any other graph. It will have vertices and edges. So the vertices or the nodes of your tree should be labeled with the states. What do we mean by states? If you remember what is a state in in symbolic execution? It is the values of the variables. So here there were two variables x and y. So each node or vertex should be labeled with those values. And then here it explains what the state is. It's a value, it's a 3-tuple consisting of symbolic values for x and y, along with, in symbolic execution, we keep a path constraint, which is what are all the conditions to be satisfied on the variables for me to reach a particular statement so far. So I keep these things in the node. And the transitions of the symbolic execution tree, the guideline was to label the transition with the given program control points. What do we mean by control points? They are just the statement numbers in the program. So using these guidelines and from the lectures, here is how you would have drawn a symbolic execution tree. Please don't worry if exactly you didn't draw it this way, but you should have got something with 8 nodes that has this kind of a branching structure. That would have been a correct symbolic execution tree. So what was the guidelines? Let's go back and look at it. The nodes, the vertices of your tree should be labeled with states. State is a 3-tuple consisting of symbolic values for x and y and the path constraint. So if you see, that's what I've done here. There were two variables, small x and small y. I have given their symbolic values with the names capital X and capital Y. So here is the first state. X, the variable small x, is assigned the symbolic value capital X. The variable y, small y, is assigned the symbolic value capital Y. I'm yet to begin execution in the program. So as always, PC stands for path constraint to start with is true. So if you go back and look at the code, this is where I am. Very first statement in the program is a decision statement. X greater than y, then you do this. If x is less than or equal to y, then you exit. So there is a branch coming out of this, which is labeled by the number 1, which is the first if statement. This is when x is greater than y. The path constraint is added to this, true, and this will just be this. So I have retained it as x greater than y. This is negation of x greater than y, which is x less than or equal to y. So in the beginning, first if statement can test positive, in which case I reach the left branch. First if statement can test negative, in which case I reach the right branch. If I reach the right branch, the execution stops there. There's nothing else in the program to execute. So we'll go back and see what happens in the left branch when the if statement is true. So I enter the if statement. If you go back and look at the program, there were 3 statements labeled with numbers 2, 3 and 4, which we discussed. They basically swapped the values of x and y. So I'm capturing them in the symbolic statement, symbolic execution tree. So after statement number 2 is executed, x becomes x plus y, y becomes y. That is true, right? Because x becomes x plus y. Statement 2 doesn't change the value of y, so y stays as capital Y. That's what is captured here. Path constraint is x is greater than y because I am within the first if statement. After the statement number 3 changes the value of y. So x continues to stay as capital X plus capital Y. Y becomes capital X. So this is where y gets the value of x. Path constraint is the same. After the third statement, you'll realize now here, see, x has taken the value for y and y has taken the value of x. Before these 3 statements were executed, you go back and look up in the node here. X was taking the value x, y was taking the value y. After executing these 3 statements, I have swapped the values of x and y. Path constraint continues to remain the same. So where are we in the program? We finished executing line number 4, statement number 4. The statement number 5 is an if statement. It says if x minus y is greater than 0, then you assert false. Otherwise, you exit. So that's the symbolic execution here. So statement 5 is an if statement. So there is a branching in the execution tree. So path constraint is whatever you had earlier. We had x greater than y earlier, if you see throughout. I am ANDing that with the new path constraint, which is y minus x. Why have I changed it to y minus x when x minus y was given here? Please remember, after the 3 statements 2, 3 and 4, the values of x and y are swapped. So x becomes capital Y, y becomes capital X. Capital X and capital Y were the symbolic execution values for small x and small y. So path constraint is x greater than y, whatever was there earlier, and y minus x is greater than 0. I've passed the second if statement. Here the path constraint is x greater than y and y minus x is less than or equal to 0. So if I pass this, I reach an error. I have not depicted that in my symbolic execution tree. If you want, you could put another node here which says that you go to line number 6 and say assert false. Because it's an error statement and asserting false leads in an abortion of execution, program execution, I haven't depicted that. So this is how the symbolic execution tree will look like. So the questions, the remaining 5 questions were around this execution tree and what happens during symbolic execution. So first question was very easy. If you've drawn the symbolic execution tree correctly, the question just asks you how many nodes or vertices are there in the symbolic execution tree. As you would see here, if you count, there are 3 here, 3 plus 3, 6, plus 2, 8 nodes in the symbolic execution tree. So the correct option was 4th option. The next question says, what is the path constraint for program execution that goes through the statements 2, 3 and 4? So let's go back, statements 2, 3 and 4. What was the path constraint? When do I reach statements 2, 3 and 4? If the if statement x greater than y turns out to be true. So the path constraint for all the 3 execution as labeled in the symbolic execution tree is x greater than y. So there were 4 options given here, x greater than y, x less than y, x greater than or equal to y or true. The correct answer is x greater than y. It's the first option. So the third question was, what was the path constraint when the program begins execution at statement number 1? Here the program segment, if you see, there was nothing to begin with, no constraints. So the path execution when I begin execution is just the constant true. That's what is given here. So the answer is true. The next question says, what is the path constraint when the program reaches statement 6? So 4 options were given, true, x greater than y and y minus x is greater than 0 and false. The correct answer, if you go back and look at the execution tree, after this is when statement number 6 is reached. So the path constraint is x greater than y and y minus x is greater than 0. That's what is given here. So the correct answer that you should have chosen was the third option. This is before the second if statement. This went off right in the beginning. Path constraint was not false. We were only asserting false. Last question was very simple. It asked, will the statement number 6 in the program ever be reachable? The answer is yes, it will be. It is simple. You don't even have to draw the symbolic execution tree. If you just go back and see this program, to reach statement number 6, I have to make this if statement true and I have to make this if statement true. I can obviously give values x and y such that this is true. So statement number 6 will obviously be reached by the program. So the correct answer to the last question in the assignment was yes, which is the first option. So I hope this video helped you to solve the assignments. Please feel free to ping me in the forum if you have any further doubts about this particular assignment. Thank you.